Okay, so let's talk about this. Today's idea is we're going to kind of combine everything that we've been recently doing with sampling distributions and kind of see like the math behind what we can do with all this stuff. So again, like before, like populations use these kind of statistics. And let's say we have a population. And let's say for some reason we need to take a sampling proportion. And when we take a sampling proportion, hopefully you remember from Tuesday that here's the kind of formulas for this. Like the proportion should be the same as the population's proportion of the sample. And then if I need to find how spread out the proportion is, this is how you find the standard deviation of that proportion. Or I wrote X, but I probably meant P hat. So this would be the standard deviation of the proportion statistic. Our means would be, which is what we're going to do today, is this. Again, the sample mean should probably be the same as the actual mean of the data unless there's some kind of bias. So the sample mean and the actual mean will be the same. And then how you find the sample standard deviation is take the actual standard deviation, divide it by the square root of how big your sample size is. So if you think about it, like our standard deviation will get smaller if we keep taking more and more samples. And that should kind of make sense from what we did today with the penny activity. Remember, when we took more and more samples, if we looked at it, the variability of the data went down. The other nice thing that will always happen is this distribution will always start to become normal the more samples we take. So if we take more and more samples, the data will eventually always become normal for these sample proportions and these sample means. Let's kind of look at a problem. So it goes, suppose that we have a random selection of 64 measurements from a population, and the mean of this is 20. And the standard deviation of this is 4. And they said, describe the shape of the sampling distribution in the sample mean. Well, the shape of the sampling distribution in the sample mean should become normal. It should always become normal because the more and more averages we take, they all should start getting closer and closer to the actual average. Do we need to make any assumptions about the actual population? No. The population actually could look something like this. And be like skewed, but it actually will eventually just line up and all the averages will just start to pool to where the main part of the data is going to be. So the sample is always normal. So this is always normal. The population does not have to be normal. It can be whatever kind of skew. We don't need to know anything about the shape to be able to know that the sample will be normal. Okay. Let's see if we can find some things. So it said, oh, find the mean and standard deviation of the sampling distribution. Well, we know that the mean of the sampling distribution from before should be the same as the mean of the population. And we said the mean of this population was 20. So the mean of the sampling distribution should be 20, barring any kind of bias or anything that we did very poorly. So that's what the average should be. And the standard deviation of this thing should be the actual standard deviation, which before it was 4, divided by the number of, the square root of the number. So we took 64. If I remember right. Yep. So our standard deviation was 4, and we took 64 different measurements. So that is the number, or the n, that we get before. If we kind of do this, that means that our standard deviation should be 4 over 8, which should give us a 0.5. Now we need to calculate the probability that we get a sample mean that's greater than 21. And obviously, we're going to have some normal distribution. Most of the sample means that we get will be around 20 right here, but we'll have some that kind of are 21, and we want to know this percent. So we want to know where that is on a curve. Well, hopefully you remember from before how we figure out that area right there. And how we do that is first we calculate a z-score. And z-scores are your x sub I minus your mean over your standard deviation. So our x sub I this time, what we want to know is 21. Our mean is 20. And we would divide this by our 0.5. That's going to give us 1 over 0.5, which is going to be really nice because that is 2. So this thing is 2 standard deviations away. Now most times we would look on the chart, so we just standardize this. So it's 2 standard deviations away. Most times we'd look on the chart, but hopefully you remember from before that between 2 and -2 standard deviations, that's 95% of the data. So if that's 95%, this and this is the other 5%, which that would be 2.5%. So the percent of the data that's right there is 2.5%. Most of the problems today, you'll calculate these z-scores, and then you probably will have to look on some kind of z-table. That'll look something like this, and this is in your pink packet. If you know the calculator commands, you can use the calculator commands. I would just recommend converting all the z-scores, just looking it up on the table, and figuring out those percentages. So try the different problems that we have today.